So this is the chemistry lesson video for section 14.4. So if you can believe it, there are still 2 more gas laws that we have to learn. So we've learned Boyle's law, Charles' law, Gay-Lussac's law, combined gas law, ideal gas law, and then there's still 2 more. So we'll have 7 total. So let's just go ahead and jump into the first one. The first one is the easiest one. So it's called Dalton's law of partial pressures, and it states that at constant volume and temperature, the total pressure exerted by a mixture of gases is equal to the sum of the partial pressures of the component gases. So in other words, our total pressure is just the pressure of each gas in the container added together. Doesn't get much easier than that. Okay, so let's say that we have this red gas, and let's say it's at 1 atm pressure. And then we have a blue gas in a different container, and let's say it's at 3 atm pressure. Well, if we put them together, what would be the new pressure? You just add it together. So it'd be 4 atm. That's all you have to do. Or it could ask us like this. It could say the red and the blue have a pressure of 4 atm. The red just is 1 atm. What's the blue? And so then in that case, we could subtract and figure out the blue must be 3 atm. So in other words, the only thing about this one is you just need to figure out, are you adding or subtracting? If they ask you for total pressure, you add the partial pressures. If they ask you for one of the partial pressures, you just take the total and subtract the other ones. That's all you have to do. Super easy. Alright, so it says air contains oxygen, nitrogen, carbon dioxide, and trace amounts of other gases. What is the partial pressure of oxygen? So in other words, we're looking for one of the partial pressures. So I'm going to call this PO2 because oxygen's O2. At 101.3 kPa, so there's my total pressure. If the partial pressures of nitrogen, carbon dioxide, and other gases are 79.1 kPa, 0.04 kPa, and 0.94 kPa respectively. So I'm just going to call this P1, P2, and P3. Or you could call it 2, 3, and 4 if you want oxygen to be P1. So in other words, all I need to do is look. Do they want the total pressure? If so, I add up all the partials. Or did they give me the total pressure and want one of the partials? If that's the case, I take the total, which is 101.3 kPa, and I subtract the other pressures from it. So 79.1 kPa, 0.04 kPa, and 0.94 kPa. Now, I know some of you are like, why in the world would I write that down? You clearly would not. You would put it in your calculator. Okay, but as the teacher, I obviously have to write it down. Okay, so once I do all that, I end up getting about 21.22 kPa. Now, the only thing you would need to be careful of on this is just make sure all your units for pressure are the same. Because if they're not, you got to make sure they're the same. Okay, so remember, the rule is if you're looking for total pressure, add all the partials. If you're looking for one of the partials, take the total and subtract the other partials from it. Okay, so let's look at a couple more. These obviously, as you can imagine, don't take a whole lot of practice. Alright, so if you're ready, I'm assuming you are. I'll go ahead and pause it and try both of them. Okay, I'll assume you've done that. So the first one, it says determine the total pressure. Well, y'all, you've learned that since elementary school. To get a total, you add up everything else. So it gave us our partial pressures right here. So all I'm going to do is just add them. Again, if this was on like a worksheet or a quiz or test or something, I don't need to see your work. Okay, just put it in the calculator. I don't even like having to write it out right now just to show you how to do it. Okay, but because I'm looking for the total, I add up my other pressures. And once I added them up, I got 93.4 kPa. And again, the only thing to look out for is just make sure everything is in the same unit, which in this case, it was all in kPa. Alright, so hopefully you got that one right, and hopefully you've already tried the bottom one. It says a gas mixture containing oxygen, nitrogen, and carbon dioxide has a total pressure of 32.9. If the pressure of oxygen is 6.6 and nitrogen is 23, what is the partial pressure of carbon dioxide? So see, they gave me the total, and they gave me some of the parts. I just need to figure out the other part. So that's where I take the total, the 32.9, and I subtract the other partial pressures. Whoops, and 6.6. And so once I do that, I end up getting 3.3 kPa. Okay, so so like I said, the two parts to Dalton's law of partial pressure are, one, make sure all your pressures are in the same unit, and two, you just need to decide, am I looking for the total? If so, add. Or did they give me the total and I'm looking for a partial pressure? If so, take the total and subtract the other partial pressures, and that's it. Okay, so Dalton's law is usually everyone's favorite because it's super easy. So now let's move on to our last one, which is Graham's law. But before we get to it, let's discuss what some vocab means. So diffusion is the tendency of molecules to move towards areas of lower concentration until concentration is uniform throughout. You see diffusion happen all the time. Well, you don't really see, you just smell diffusion happen all the time. So let's say somebody in one corner of the room, and you know it always happens, like right before the bell's about to ring, some girl gets out this nasty smelling cheap perfume and she starts spraying it all over herself. And so then the people right around her start smelling it first, but everyone across the room doesn't even know what's happened yet. And then they start raising, oh, Miss Porter, somebody just sprayed something. I'm like, yes, I know. And then it slowly starts spreading. And in the middle of the room starts raising it. Somebody's spraying something. And I'm like, yes, I know, y'all. Somebody sprayed perfume. And then finally on the other side of the room, they smell it. And by the time the bell rings, my whole room now smells like her terrible cheap perfume. And she's out in the hall. So why does this happen? Well, it's diffusion. When she sprayed the perfume, there was a high concentration right around her. And so there was a low concentration throughout the rest of the room. The rest of the room didn't have any of her perfume. And so what happens is that perfume slowly spreads throughout the room. Sometimes I get lucky and somebody sprays something that smells good and then it spreads throughout the room. But many times it's not something I really like. So just as a rule of thumb, just spray your perfume when you get outside the room. So during effusions, that's diffusion, from high to low concentration. During effusion, a gas escapes through a tiny hole in its container. So an example of effusion would be like a balloon. So you know how if you get a helium balloon, it floats nice and high, and then a couple of days later though, it's kind of like lowered a little bit, but it's still floating, and then it eventually gets to where it's not floating at all, it's laying on the ground, and then a couple of days later, you'll notice it starts shrinking. A lot of people think that the gas, the helium, is escaping through where you tied the balloon, but it's actually escaping through the balloon itself. The rubber or latex or whatever type of balloon you're using, it has tiny, tiny holes in it, especially when you stretch it. And so that helium is slowly infusing or escaping through tiny holes in the balloon. Gases of lower molar mass will diffuse or effuse faster than the heavier gases of higher molar mass. Okay, so that makes sense. The lighter or lower molar mass gases can escape faster than the heavier ones. All right, so in other words, what we're about to do is work on some molar mass. So hopefully you remember what that is. So Graham's law of effusion or diffusion states that the rate of effusion of a gas is inversely proportional to the square root of the gas's molar mass. Now, I'm technologically disadvantaged and everything, so I couldn't figure out how to do like a gigantic square root here, so I just raised it to the 1/2. So I'll just rewrite it over here with the square root though. So it's the rate of gas A over the rate of gas B equals the square root of the molar mass of gas B over the molar mass of gas A. Okay, so here's our formula, and I did not accidentally switch those. It's A over B on one side, B over A on the other side. To make their answer make sense, we always choose B to be the bigger or more massive gas, and so I'll show you what I mean by that once we get to some. All right, so let's look at what it says. So it says compare the rates. So if they ask me to compare the rates, I'm going to solve for this whole side. Like I'm not just going to, it didn't ask me what is rate A or what is rate B. It said compare the rates. So really all I need to do is plug in the molar masses. So it says compare the rates of effusion of helium and nitrogen gas. So the first thing I would do is write the formula. So helium is He. Nitrogen is N. Is it N? Are you sitting there thinking, well, yeah, it's N? Or are you thinking, ooh, Miss Porter's just made a mistake? Well, of course I didn't make a mistake. I know it's not just N. I'm hoping you knew it wasn't just N. N is diatomic, so it's N2. Okay, so hopefully you caught that. If you didn't, shame on you. Learn your diatomics. All right, so we need the molar masses of these because I told you B is going to be the more massive gas. So if you look at the periodic table, helium is 4 grams per mole, and nitrogen is 14. But because it's diatomic, it's 28. Know your diatomics, people. Remember, start at number 7, which is nitrogen, make a big 7. NOFClBri, and then you gotta remember hydrogen. Alright, so because N2 has the larger mass, I'm gonna make that gas B, and I'm gonna make helium gas A. Alright, so my rate of A, or in this case helium, over my rate of B, or nitrogen, is the square root of the molar mass of B, which is my nitrogen, 28 grams per mole, over the molar mass of A, which is helium, which is 4 grams per mole. So if you look, my grams per mole cancel, and we didn't make it a percentage. So like for the first time ever, there just are no units to this number. So I do 28 divided by 4, which of course is 7, and then I do square root of 7. I'll go ahead and tell you, a common mistake is people will put 7 as the answer. They forget to do the square root. Alright, so I end up getting 2.7. No units. However, there's still something that counts as your units, and that is the sentence. It says compare the rates of effusion. Well, what does 2.7 mean? That's not comparing anything, that's just showing me a random number. So you have to write a sentence, and the sentence is the same every time. It's whatever gas A is, diffuses or effuses, it just depends on what it asks you in the question. Whatever your number is, times faster than gas B. Okay, so then I just fill in. So what's gas A this time? It's helium. So helium, it says effusion. So it fuses my number, which is 2.7, times faster than gas B, which in this case is nitrogen, or N2. Okay, so once you get your number, that's fine. That's half credit. The other half of your credit comes from writing your sentence. So whatever gas A is, diffuses or effuses, whatever number you calculated times faster than gas B. That's why we always pick B to be the more massive gas, so that way you get a number greater than 1. It doesn't make sense to say something goes 0.5 times faster, because that's really saying it goes slower. Okay, so helium effuses 2.7 times faster than nitrogen. And that's all you have to do. Okay, so let's look at another one. And watch out for those diatomics. I'm telling you, those diatomics will get you. Alright. So, maybe try this one on your own, or watch me do this one and then you can try the bottom one. I'm going to leave my sentence up though, even though I know it blocks part of this. Alright, so it says compare the rates of effusion of sulfur trioxide, so sulfur trioxide is SO3, and bromine gas, which is Br. Or is it Br? No, it's Br2 because it's a diatomic. If you didn't put that, you're going to get it wrong. Alright, so then I add up the molar mass of each of them. So S is 32, O is 16 times 3, which gives me about 80 grams per mole. Now, if you had put bromine gas as Br, you would get 80 grams per mole again. And so then you'd be like, well, what do I do? They're the same. That means you did something wrong. Okay, because bromine's Br2. So it's 80 times 2, which is 160 grams per mole. So because bromine has the heavier or more massive particles, it's going to be gas B, and my sulfur trioxide is going to be gas A. So now I'm ready to plug into my formula. So my rate of A, or my rate of sulfur trioxide, over my rate of B, which is bromine, which is Br2, because it's diatomic, equals the square root of the molar mass of B, which is my bromine, 160 grams per mole, over the molar mass of A, which is my sulfur trioxide, which is 80 grams per mole. So my grams per mole cancel, so I do 160 divided by 80 and square root that. Don't forget to square root it. I get 1.41, so there's half of my credit because I got my number, but now I have to write my statement. So gas A, which in this case is sulfur trioxide, so SO3. In this case it asks me about effusion. It fuses 1.41 times faster than gas B, which in this case is Br2. And there you go, that's it, okay? So you try the bottom one, pause it, I'll assume you've done that at this point, and so let's look at it together. Alright, I'm going to have to erase this though so I can write on this one. Alright, so it says compare the rates of effusion of oxygen gas. Oxygen is O2, 2, hopefully in your mind you're like, oh, she needs to stay at 2, because it's diatomic, and carbon dioxide gas. So carbon dioxide is CO2. So the first thing is we need to add up those molar masses. So oxygen 16, so 16 times 2 is 32 grams per mole. Carbon dioxide, C is 12, O is 16 times 2, so it's 44 grams per mole. So because of that, carbon dioxide is going to be gas B, oxygen is going to be gas A. By the way, I just noticed I didn't mean to make it a pattern, so an unintentional pattern. The second gas is not always going to be the more massive one. It just happened to be in my 3 examples. So just always make sure you know which one's A and B. Alright, so then I plug in. So my rate of A, which is oxygen, over my rate of B, which is carbon dioxide, equals the square root of the molar mass of B, which is 44 grams per mole, over the molar mass of A, which is 32 grams per mole. And remember, y'all, you don't have to sit there and write all this out. If you can do it in your calculator, just do it in your calculator. I don't care. I just want you to get the right answer and know what you're doing. All right, so 44 divided by 32, and then square root that. That gives you 1.17. So there's half your credit, and then you have to write your sentence. Okay, so gas A, which is oxygen, effuses 1.17 times faster than gas B, which is carbon dioxide. Alright, so hopefully you got that right. So see, the last 2 gas laws, they aren't that bad. Alright, so main thing is don't forget those diatomics because they will throw you off. Other thing is don't forget to do the square root part. A lot of people, they just divide, and even though they wrote the square root on their paper, they didn't actually put the square root in the calculator. Alright, so let's knock out this section assessment. So in a mixture of gases, how is the total pressure determined? Well, the total pressure is determined the way every total is. You add up the partial pressures. That's it. Add up the partial pressures. Number 2, what is the effect of molar mass on the rates of diffusion and effusion? The larger the molar mass, the slower it diffuses or effuses. Okay, so the larger the molar mass, the slower it diffuses or effuses. That's something on my board right there. Number 3, what distinguishes effusion from diffusion and how are they similar? Well, what distinguishes them is diffusion can happen anywhere. Effusion is a gas escaping a small hole in a container. Alright, so diffusion, it can just happen anywhere. Effusion is specifically when a gas escapes a small hole in a container. How are they similar though? They both go from high to low concentration. Okay, so a lot of people think they're different by, they'll say diffusion goes from high to low, so effusion must go from low to high. Effusion is really just like a specific type of diffusion. Okay, but they're similar in that they both go from high to low concentration. And then number 4 says, explain why the rates of diffusion of nitrogen gas and carbon monoxide are almost identical at the same temperature. Okay, well remember, we know effusion depends on molar mass, so let's look at them. Well, what's nitrogen? You should know now, it's N2. And so nitrogen's 14 times 2, so it's 28 grams per mole. And then it says carbon monoxide. Well, carbon monoxide is CO. Carbon's 12, oxygen's 16, so that's 28 grams per mole. So the reason that their rates of diffusion are almost identical is because the molar masses are the same. Okay, so that's what you can put for that one. The molar masses are the same. And remember, your rate of effusion and diffusion is based on molar mass. Alright, so that concludes our 7 gas laws, which I'm sad about because I love gas laws. It's like one of my favorite chapters. But anyway, so hopefully you're not doing too bad with the math. Hopefully a lot of people find that plugging into a formula is easier than like stoichiometry where you have to plan your way through the process. So hopefully plugging into the formula is helpful, but if you need help, obviously always contact me.